In this video, we're going to focus on section 2.6, which talks about other types of problems, including radical equations and absolute value equations. Let's get started after I share my screen. What we're seeing here in problem number 1 is what's called a radical equation. You can see on the left that there's a radical with an expression underneath it involving the variable x. On the other side, there may be another radical equation, or there could be just a constant. There could also be an x term over there. These are what are known as radical equations. Let's see how to solve them. We're going to start by rewriting the problem as we always do and numbering it to be sure that we keep it in order so that I can grade it more easily. Remember, a crabby professor is not a generous professor. Now we have to do something kind of risky in order to solve these. We're going to have to isolate the radical and then square both sides of the equation. When we square both sides, we introduce the possibility of having what's called an extraneous solution, which is a false solution. We get the answer when we solve the problem, but if we try it in the original problem, it won't work. And this is a result of squaring both sides. Why does squaring sides produce an extraneous solution sometimes? Well, it's because when you square something, you lose the information about whether it was positive or negative. And so because of that, there's a possibility, not a guarantee, but a possibility that we'll get a false solution. So step 1 is to isolate the radical. Now, if you have two radicals, you're going to have to choose one of the radicals to isolate. You won't be able to isolate both at the same time, probably. So you choose one to isolate, and then you square the sides, not individual terms, the sides. So that means that we go from the beginning of the equation to the equal sign, and we put a square. And then from the other side of the equal sign to the end of the problem, and we put a square. This means if there are two other terms on one side, that we're going to have what looks like a binomial type thing being squared. And we'll have to use the process of FOIL in order to multiply it out. In this case, we only have two terms, the radical and the 4. When we square the radical, it lifts off and we get x minus 5 equals 16. Now, we're going to solve this problem by moving the negative 5 by adding 5 to both sides of the equation. This gives us x equals 21. Don't circle it yet. There's always a possibility of a false solution called extraneous, and I'll spell it for you in a moment. What we're going to see now is we're going to test whether or not it actually works in the original problem. If it works in the original problem, then we circle it. If it doesn't work, then there's no solution. So now we're going to test. Testing is not optional on radical equations. It's mandatory. Now we're going to have the square root of 21 minus 5. Does that really equal 4? Well, 21 minus 5 is 16. And the square root of 16 is the principal square root, noted because out front there is no sign, which means it's the positive root, which is 4. Then we get 4 equal 4, which checks. That means that x equal 21 is our solution to this problem. Let's put the answer in and see what we get. Perfect. Now let's go on to the next problem and see what this one has for us. In problem number 2, you can see that we have more than 2 terms. In fact, we have 3. We have the radical, which is 9x minus 45. Then we have the term x by itself, and then the term negative 3 by itself. Remember, terms are separated by plus signs, minus signs, and equal signs. But the plus and the minus have to be out in the open. They can't be buried under a radical. They can't be inside a fraction, and they can't be inside parentheses. They have to be out in the open. We only have one radical term, which means we're going to isolate the radical term, and then we're going to square sides, not terms, sides. So first we isolate the radical. In this case, it's already isolated because we have the radical term by itself on one side on the left. Now we're going to square the sides. Again, on your exams, I would like you to write something out to the side, and on the homework that you write up for discussions, I'd like you to write out something to the side to let me know what led you from one line to the next. Now we put parentheses around each individual side of the equation, from the beginning to the equals and square, from the equal to the end of the equation and square. In other words, we're not squaring x and we're not squaring -3 just by themselves. We're squaring the quantity x minus 3. That means that we're going to have a binomial times itself. If it helps you, go ahead and write it twice. There's no penalty for writing it out. I'll be honest with you, it helps me if I write it out. And that way I can be more sure that I'll make fewer careless mistakes. On the left, squaring the radical lifts it off, and we're left with 9x minus 45. On the right-hand side, on the other hand, we have that binomial squared, so we have to multiply it out using the distributive property, or what in America we tend to call the FOIL process. The first products give us x squared. The outer product is -3x. The inner product is -3x. And the last product is a +9. Now, in order to solve this equation, we're back to a previous section, which basically means we have choices. The first thing we need to do is get everything on one side and 0 on the other. Since x squared is positive where it is, I'm going to leave it here and move the 9x and the -45 to join the rest. Then I'm going to swing the equal sign and the 0 to the opposite side. I have -3x and -3x, which is -6x, minus 9x would be a -15x. 9 plus 45 would turn out to be 54. Then I'm going to swing the equal 0 around. Why? Just because I like it better on that side. That's really the only reason. Now we have a choice. We can solve this equation by factoring. We can solve this equation by completing the square on x squared and -15x, or we can solve this equation using the quadratic formula. It's not set up to do the square root property immediately because we have an x term and an x squared term. The square root property only works once you have the variable term in one place only and it's squared. In this case, I'm going to use factoring. I'm going to form A times C, where A equals 1, B equals -15, and C equals 54. A times C is going to be 1 times 54, which is 54. The last sign is positive, which tells me I have the same sign inside the two binomials, and I'm taking a sum. Then the fact that this is a negative tells me they're both negative. I'm going to write down the different factors of 54. 1 and 54, 2 and 27. Let's see, does 3 go in? 5 plus 4 is 9. 9 is divisible by 3. Yes. 3 times, well, 3 goes into 5 once with the remainder of 2. 3 goes into 24 8 times. I'm looking for a pair that sums to give me 15. I haven't reached it yet. Does 4 go into 54? No, it doesn't. 5? No, it doesn't end in a 5 or a 0. 6? Yes. 6 and 9. Ah, there's my pair right there. 6 plus 9 is 15. So then I'm going to rewrite the middle term, -15x, as -6x minus 9x. Note that the signs remain the same and they're both negative. This gives me a way of factoring by grouping, where I pull the first two together and the second two together. The common factor out of the first two terms is x, leaving behind an x minus 6. The signs on the second pair don't match the order of the signs on the first pair. This was positive, negative, looking at the first one. And this is negative, positive, looking at the second pair. So I'm going to take out the negative. When I take out a -9, it's like dividing out a -9. And 54 divided by -9 is a -6. Notice that the two binomials are now identical, signs included, so I know the method worked. Then I factor out the binomial common factor x minus 6, and what's left behind is x minus 9. Remember, I'm trying to solve a quadratic equation, so the next thing I do is I set each factor equal to 0 and solve. This is due to the zero product property. It says that if you have two factors multiplied to give you 0, one of them must be 0. This does not work for any number other than 0. That's why 0 is in the name. And that's why we insist on having it equal to 0 at the beginning. Then we add 6 to both sides, and that gives us x equals 6 as one possibility. Add 9 to both sides, and that gives us x equal 9 as another possibility. Don't circle the answers. Remember where we started. This was way back up here, a radical equation. Radical equations always have the possibility of false solutions. We're going to start with the original equation, which is right here, and we're going to test each solution to see if it really works. Now I'm going to test x equals 6. This gives me the square root of 9 times 6 minus 45. Is that really equal to 6 minus 3? 9 times 6 would give me 54. 54 minus 45 gives me 9. On the right side, I get 3. Is the square root of 9 equal to 3? Yes, the square root of 9, the principal square root, which is the positive one, is 3. So I know that the solution x equals 6 definitely works. Let's check x equal 9. Now I take and I have 9 times 9 minus 45. Is that really equal to 9 minus 3? 9 times 9 is 81. And that gives us 81 minus 45. And 9 minus 3 gives us 6. 81 minus 45 would be borrowing, would give me 7 and 11. So 11 minus 5 gives me a 6. And 7 minus 4 is a 3. And the question is the principal square root of 36 equal to 6? And the answer is yes, it is. In this case, both solutions worked, so we can circle them. Don't make the assumption that because it worked in both the first two problems that it always works. It's often the case that when you get two possible solutions, one at least does not work. It is possible that neither works. So now we have the solution 6, 9. Let's see if we can find another one. Let's take a look at this problem right here. This is problem number 3. In looking at problem number 3, notice that the radical is not isolated in the beginning. You have the term -7 sitting next to the radical. Before you square sides, you have to isolate the radical. So step 1 is going to be isolate the radical. That means I'm going to move the 7 to the opposite side of the equation by adding 7. That gives me the radical x minus 4 equal to 11. Then I'm going to square sides. And that's going to lead me to lifting off the radical on the left and squaring 11 on the right. That gives me x minus 4 equals 121. Then I add 4 to both sides to obtain the final possible solution, 125. I have to check it in the original problem, which is here, to be sure it works. 125 minus 4 minus 7, does that really equal 4? Now 125 minus 4 would give us 121. Note that I'm writing the equation exactly as it appeared in the original. Now the square root of 121 is 11. Then we have 11 minus 7, and the question is that really 4? And the answer is yes, it is. What typically happens when you get an extraneous solution is that you have the same number value, but opposite signs. In other words, it would say something like 4 equal negative 4, which is false. And that would lead to an extraneous solution, and there'd be no solution. Because it worked, we can circle x equal 125 and give that as our solution. Let's take a look at this more difficult problem in number 4. In number 4, what we can see is we have 2 different radicals. This is going to make the problem more complicated. In fact, it's going to lead us to have to isolate and square twice instead of just once. Let's write the problem down and get started. We have the radical of 3x plus 7 plus the radical of x plus 2 equal to 1. In order to apply the process to solve a radical equation with 2 radicals in it, we have to still isolate one of the radicals before we square. If we squared now, we wouldn't get rid of the radical because it would simply move to the middle term. So we're going to isolate one of them. It doesn't matter which one you isolate. I tend to isolate the one that's more complicated if it makes no difference, or the one that's easier to isolate. In this case, I'm going to choose to isolate the 3x plus 7. So we're still isolating the radical. The next step is going to be to subtract the radical square root of x plus 2 from both sides. This is going to lead to the radical of 3x plus 7 equal to 1 minus the radical of x plus 2. I chose to put the radical second because it was negative. You can also put it first and then put plus 1. When I'm looking at this now, I've got one of the radicals isolated on the left and the other radical, plus or minus a term, on the right. Now I'm going to square sides. When I square sides, I again start at the beginning and go to the equal sign and square. That's going to lift off the radical of the one on the left and give me 3x plus 7. On the opposite side, I also start at the equal sign and go to the end of the equation and square. Unfortunately, we cannot square individual terms. That will not lead to a true statement. Whatever is done has to be done to sides, not to terms. In this case, when I write this, I can write it out twice to help me to do the multiplication. When I do FOIL, or the distributive property, I get 1 times 1 for the first, which is 1. On the outside, I get 1 times the negative radical, which will give me the negative radical. On the inside, I have the negative radical times a 1 again, which gives me the negative radical again. Now I have the last product, which is the negative radical times itself, which squares it. When I do that, I have a negative times a negative, which is a positive, and the radical times itself gives me the radical squared. What that's going to do is lift off the radical and give me the expression under the radical, x plus 2. Let's go ahead and combine our like terms and rewrite the equation. I have 1 minus 2 square roots of x plus 2 because the outside and inside products double. Notice the radical didn't disappear completely. It turned up in that middle term. The last term becomes x plus 2, what was under the radical because it got squared when I multiplied it by itself. Now I am starting all over essentially. I have another radical equation and I need to isolate the radical and square the sides. That means that I need to move my like terms to be together. So the next thing I'm going to do is subtract, wait a minute. I've got a 1 and a plus 2 that's both on the right side. I should probably clean this up a little bit. Let's go ahead and simplify a little bit and combine our like terms that are already on the same side. I have an x, the 2 plus 1 gives me plus 3, and now a minus 2, the square root of x plus 2. I'm going to have to isolate this radical term. I don't particularly like isolating negatives, so my inclination is to move it to the left. What's yours? It is okay to isolate it even when it's negative, but then you'll have to divide by a negative. Now let's take a look and let's see what we get. I'm going to move it because I don't like the negative. That means I'm moving the radical term to the left side of the equation by adding 2 the square root of x plus 2 to both sides. That also means I need to move this 3x plus 7 to the right side by subtracting 3x and subtracting 7. Notice my equals is right here, and I'm keeping it balanced by doing the same thing to both sides of the equation. This puts the radical expression on the left, 2 times x plus 2, and the variable terms, now negative 2x minus 4, on the right. Now I can divide everything on both sides of the equation by 2. That will isolate the radical further. When I divide by 2, I end up with the following expressions. Again, it's a weird thing in math, but the more you write, the faster you work and the more accurately you work. You don't get any bonus points for doing things in your head. Whereas a tendency in high school to think that the person who could do it in their head was the smartest, that does not play out in college. The smartest person is the person who writes more down because they make fewer mistakes. And that really has nothing to do with intelligence. That just has to do with being careful. This gives us the square root of x plus 2 equal to negative x minus 2. Now I've isolated the radical, I'm allowed to square sides again. Notice that because the original problem had 2 radicals in it, I've had to square sides twice. From the beginning to the equals and square, from the equals to the end and square. It lifts off the radical on the left, and I'm going to have to multiply this out in order to see what I get on the right. Again, it helps me to write it twice. If it doesn't bother you not to, you don't have to. But if it helps you, then do it. Negative x times negative x is a positive x squared. On the outside, negative x times negative 2 is a positive 2x. On the inside, negative 2 times negative x should be another positive 2x, since the outside and inside should be the same and should double. Negative 2 times negative 2 would be a positive 4. Now let's clean up the like terms that we have here on the right side. Now we have a quadratic equation, and we need to solve the quadratic equation. In order to solve the quadratic equation, we have 4 basic techniques. The square root property, which won't apply here because we have the variable x in multiple terms. Completing the square, which can work here, or factoring, solving by factoring, which might work here, or using the quadratic formula, which would also work here. Remember, completing the square and using the square root property after and the quadratic formula are the two methods that never fail. In order to solve it, I need to get all my terms onto one side. So I subtract the x and subtract the 2. This leads to x squared plus 3x plus 2. I'm going to swing my equals 0 around because it just bugs me to have it on the left. Now, looking at this problem, I think it might factor. So I'm going to try factoring first, this time using the trial and error method or the intuition method. I know x squared splits up as x and x. Then I look at the last sign, which is a positive, which tells me they're the same. And the middle term then tells me they're both plus. I know that 2 can only split up as 2 times 1. So there's really not any other option for factoring. I do want to check to make sure that the outside and inside products do add, because of the last sign being plus, to give me 3x. And they do. Now I use the zero product property, which says if they multiply together and give you 0, one of them has to be 0. We have 2 possible answers, and it's been a long time since we started this process. What was the original problem? Oh yeah, it was a radical problem. Radical problems have the possibility of extraneous solutions, so we can't circle them yet. We need to make sure that they both work. We're going to rewrite the original problem and we're going to test each one. Testing x equal -2 means replacing the variable x with -2 in the original problem and seeing if it gives you a true statement. In this case, I get 3 times -2, which is a -6. -6 plus 7 is going to give me the square root of 1. -2 plus 2 gives me 0, so I have the square root of 0, which is 0. This gives me 1 equal 1, which definitely checks. And that lets me know that it does in fact work. That means that x equal -2 is a solution, so I can circle that one up. That doesn't mean the other one works. Now we have to test the other one, which is -1, back in the original. It was -1, wasn't it? Yes. Now we're going to test -1. 3 times -1 plus 7 plus the radical of -1 plus 2. Does that really equal 1? 3 times -1 gives me a -3, plus 7 would give me 4. In the second problem, -1 plus 2 gives me 1. That would be 1. The square root of 4 is 2, and 2 plus 1 gives me 3. And I've got a problem because 3 does not equal 1. This is the first time we've seen an extraneous solution. Note here that x equal -1 does not work. It leads to a false statement, and we call this an extraneous solution. It's kind of a contradiction in terms because an extraneous solution is not a solution at all. It doesn't work. The only solution here is -2. So in web work, the only one you put in is -2. Let's take a look now at different types of problems, which are absolute value problems. Absolute values come up in all kinds of applications because they're talking about the distance of something from something else. That's the way that we're going to interpret the absolute value, as a distance. Let's look at the basics, starting with problem number 5. In problem number 5, we have the absolute value of x plus 6 equals 6. When we see absolute values, we're going to replace the absolute values and say instead, absolute value is the distance. So how would I read this particular problem? The distance of x plus 6 from 0 on the number line is 6. That's really what we mean when we talk about an absolute value. Absolute value is how far it is from 0 on the number line. So x plus 6 can be 6 away from 0 on the number line. Let's draw that situation so we can understand what it means. When you draw a number line, you have arrows at each end, and you have 0 as sort of a guide to where you are on the number line. Now I'm saying that the distance that x plus 6 is from 0 is 6. So it could be 6 steps to the right at 6, or it could be 6 steps to the left at -6. Either x plus 6 is sitting here or x plus 6 is sitting there. It's sitting in one of those two places. Our job isn't to figure out where x plus 6 is. Our job is to figure out where is x so that x plus 6 sits at one of those two places. So what we do instead is we then write down what this picture represents. X plus 6 is either truly at 6 or x plus 6 is sitting at -6. Now, what led us to do that? First, notice that in the pattern that we've been following quite a bit in this course, we have isolated the absolute value so that we could say that the distance of the interior of the absolute value from 0 on the number line was equal to this number. So isolating the absolute value is the first step. Then you can say that the distance of the interior from 0 on the number line is equal to that number there. And you can split and put the interior equal to that number or the interior equal to its opposite. Then we solve each problem separately. In this side, I'm going to subtract 6 from both sides, if I can get my pen to work, and that will give me x equals 0. On this side, I'm going to subtract 6, and that gives me x equal -12. Now let's see if this really works. What happens if I say that x is 0? If x is 0, then I get 6, which means that x plus 6 was sitting up here at 6. If x is -12, then -12 plus 6 is -6, which means x plus 6 is sitting here at -6. So when x is 0 or -12, x plus 6 sits here or here. And that's exactly what we mean. These are the two solutions that we have to this problem. Let's take a look at a different problem. This is problem number 6. In problem number 6, we have the absolute value of x plus 8 minus 2 equal to 8. The first step is always to isolate the absolute value, just as it was to isolate the radical. So we need to isolate. That means the -2 needs to be added to both sides of the equation to get it away from the absolute values. The absolute value of x plus 8 then is equal to 10. What does that mean? That means on the number line, either the distance it is from 0 is 10 or 10 steps to the left at -10. X plus 8 is either here or it is here. Again, we're talking about the distance from 0. This distance equals 10. That's the way to interpret an absolute value, the distance from 0 on the number line. So now that tells us that either x plus 8 is sitting at 10 or x plus 8 is sitting at negative 10. Then we can solve the two sides separately, and this leads to x equal 2 or x equal negative 18. Again, if you test the problems and you plug them in, if you have 2 plus 8 is 10. So x plus 8 is truly sitting here at 10. If you have negative 18, x plus 8 is sitting at negative 10, which is also 10 steps away from 0 on the number line. These are our two solutions, 2 and negative 18. Notice that there is not a possibility of false solutions here as there was in the radical equations. Let's take a look at this one right here. This is kind of a weird one. This one says the distance that x plus 2 is from 0 on the number line is 0. What? Okay. The absolute value is isolated. That's always step 1. And then step 2 is to think about what it means on the number line. Well, it means that x plus 2 is sitting there. Well, if x plus 2, well, then it hasn't moved away from 0. So if x plus 2 is sitting at 0, there's no two sides. There's just the one. That means that x plus 2 has to equal 0. And that means if I subtract the 2, that x has to equal negative 2. Well, that makes sense. To get x plus 2 to sit at 0, x has to be negative 2. Let's take a look at a more complicated problem with more terms and a more complicated interior to the absolute value. This is problem 8. Again, before you drop the absolute values, you have to first isolate the absolute value. Don't say that it's either at 17 or negative 17. Whoa, totally wrong. That's because the plus 7 is not part of the absolute value. You have to isolate the absolute value so you can replace it with the distance from 0 on the number line. That means the minus 7 has to move. The true distance that 3y minus 7 is from 0 on the number line is 10, not 17. What does that mean? Again, if we're looking at the number line, that means we have 10 steps to the right and 10 steps to the left. And either 3y minus 7 is sitting here or 3y minus 7 is sitting there. The question for us is, where is y that makes that happen? Well, that just means, now that we have it isolated, that 3y minus 7 is truly sitting at 10, or 3y minus 7 is truly sitting at negative 10. And then we can solve the two separately. In this case, we're going to add 7 to both sides of the equation, and then we have 3y equals 17. Dividing both sides by 3 gives us 17 thirds, which isn't a very nice answer, but it is an answer, and it is in fact correct. On the other equation, we also add 7 to both sides of the equation, and this time we get 3y equals negative 3. Then we divide both sides by 3, and we get that y is equal to negative 1. Those are our two possible places for y to sit to make 3y minus 7 be at 10 or negative 10. Let's check it and see. If I replace the y with 17 thirds, 3 times 17 thirds, the 3's cancel and I get 17. 17 minus 7 is 10, so it'd really be sitting here. If I replace y with negative 1, 3 times negative 1 is negative 3, And -3 minus 7 is -10, so it's sitting here. In other words, if y is 17/3 or -1, 3y minus 7 will be at 10 or -10. Now let's take a look at one where we have something multiplied by the absolute value. Again, the steps are not going to change. We still need to isolate that absolute value. We're looking at the equation 2 absolute value of x plus 4, quantity minus 6 equal 10. Our step is again to isolate the absolute value. The first thing I'm going to move is anything added or subtracted to the absolute value term. They're less tightly attached, if you want to think of it that way. So I add the 6 to both sides of the equation, and that gives me 2 absolute value of x plus 4 equal to 16. I still need to isolate the absolute value. It's not isolated yet because I have a 2 attached to it. It's more tightly attached because it's multiplied. It would be the same if it were divided. Now I'm going to divide both sides of the equation by the number 2. That will remove it from the absolute value. But because I've done the same thing on both sides, I have kept the equation in balance. And in balance means that the equation has the same solution as the previous line. Now I've isolated the absolute value. My next step is to replace it with the distance from the 0 on the number line. So when I think about the number line, I've got 0 in the middle, and this says that either x plus 4 is sitting up here at 8 or x plus 4 is sitting down here at -8. That's 8 steps away from 0 on the number line. So I can write that x plus 4 is either sitting truly at 8 or x plus 4 is sitting down here at -8. And then I solve to see where x is to make x plus 4 do that. By subtracting 4 in each of the different equations, I get possible solutions of 4 and -12. If x is 4, let's put it into the original problem, which is over here. 4 plus 4 is 8, and the absolute value of 8 is 8. 8 times 2 is 16, and 16 minus 6 is 10, which checks. What about if x is -12? -12 plus 4 is -8, but the absolute value is 8, and 8 times 2 is 16, and 16 minus 6 is 10. These are our two solutions. We don't get extraneous solutions with absolute value problems. The only thing you have to watch out for are careless mistakes. Let's take a look at the next problem, trying to decide if I wanted to work it or not. And I definitely do, because something weird happens here. Okay, we have the equation 3 absolute value x plus 1 plus 14 equal -1. I can't decide where it's supposed to be or how far it is from 0 on the number line until I've isolated the absolute value. That's step 1. That means that I need to move the 14 first by subtracting it from both sides of the equation. That leaves me with 3 times the absolute value of x plus 1 equal to -15. It's still not isolated, so I still need to isolate again by divide by 3. Now I have the absolute value isolated, and I have the absolute value of x plus 1 equal -5. What does that mean? We draw our number line and we think about the distance from 0 on the number line. And now you ought to be coming to an extreme halt and going, oh, Professor D, something's not right. Because this says the distance that x plus 1 is from 0 on the number line is a -5 steps away. I don't know about you, but I've never been a -5 steps from anything. I've been 5 steps, but I've never been a -5 steps. How can you be a -10 miles from somewhere? You can't. You're 10 miles. Distance is strictly positive. What we have here is a distance, which is always positive or at least 0, equal to a negative. Not negative equal to negative. Wait a minute. Absolute values are not negatives, and it's equal to a negative. What does that tell you? Well, it tells me there's no solution. This can't happen. If I isolate and I end up with an absolute value equal to a negative, then I know there's no solution. This is a non-negative because it can be 0 or it can be positive. And the right side is a negative. Well, there's no way that's equal. If it's not negative, it can't be negative. And so there's no solution. Up here, we're to enter the words none if there's no solution. The next problem is similar, and I'll leave it to you to do this one. Note that although this starts with a -13, it would be tempting to say from the beginning there's no solution. When you move the 5, you'll still have a negative, but then you have to move the -8. And a negative divided by a negative will give you a positive. So this one should have a solution. This one is different in that we've got a fraction. However, notice what's happening right here. To isolate the absolute value, we would need to add 10. When we add 10 to this side, we still have a -6. Absolute value equal to -6. Non-negatives do not equal negatives. This one has no solution. And I can see that by inspection. Now let's take a look at another type of equation. This is a fractional exponent. Now, you should have studied fractional exponents in the previous course, but maybe it got to the end of the semester and they were rushing and they didn't do a very good job, or they skipped it. Or maybe you just don't remember. So let's review it. Looking at problem 13, we have x to the 5/6 power equal to 32. What does that mean? Okay, when we look at a fractional exponent, let's break it down into the two parts that it consists of. There's a numerator and there's a denominator. The numerator is on top, denominator is on bottom. When we're looking at the numerator, the 5, that's a power like it always is. That's x to the 5th power. The denominator, however, actually represents a radical. In this case, the 6th root. So this means that what we actually have here is the 6th root of x to the 5th. That's the way to interpret a rational exponent. Remember, the word rational, the first 5 letters spells out ratio, and that means that we have an integer to an integer. A rational exponent has a power in the numerator like normal, and the denominator represents a radical with that index. We can also write this as the 6th root of x and then raise it to the 5th power. Now, neither of these is going to help me solve this problem exactly. I've got x to the 5/6 power equal to 32, and I want to know what x is. Well, now we need another property of exponents. We need to remember how to raise a power to a power. When we have 2 powers on the same base, what's the rule? When we have 2 powers on the same base, the rule is to multiply the exponents. In other words, I want the power on x to be a 1. So I think about the number that it would take in order to multiply that power by a power and get rid of the 5/6 power. In order to get 5/6 to equal 1 through multiplication, I multiply by the reciprocal, which is 6/5. In other words, I'm taking the first and I'm raising it to another power. This means that I have the base x being raised to the 5/6 power and also the 6/5 power. The reciprocal of this, when multiplied, will give me a positive 1. But I've changed the equation if I don't do the same thing to the opposite side. So what I have to do is take 32 and also raise it to the 6/5 power. That keeps the equation balanced, which means that the solutions are the same, although the equation looks different. Now 5/6 times 6/5 gives me x to the first power. And on the right side, I have 32 to the 6/5 power. I take 32 and I use the denominator power to write it as the 5th root of 32. And then I'm going to raise it to the 6th power. It's much easier to break it down using the radical first and then raise it to the power. First off, I have no clue what 32 to the 6th power is, but I do know what the 5th root of 32 is. That's the number multiplied by itself 5 times that gives me 32, and it's 2. Then I get 2 to the 6th. Well, if 5 2's give me 32, one more 2 will give me 64. So my final solution is 64. Let's take a look at a more complicated problem, which has an expression involving the variable inside parentheses and a rational exponent on the outside. Again, the process is essentially the same as it was in the previous problem. The variable is in here and is being raised to a rational exponent. I want the rational exponent to disappear, so I raise the entire side of the equation to the 3/2 power, which is the reciprocal of 2/3. But what I do to the left side of the equation, I have to do to the right side of the equation, or I've changed the solutions, and that unbalances the equation. Now, the 2/3 to the 3/2, when we have two powers on the same base, we multiply the powers. 2/3 times 3/2 gives me 1, so I end up with x plus 4 to the first power. On the right, I can use the denominator to represent a radical. This would be the square root of 9, and you don't have to write the 2, but you can write the 2. It is the square root, and then raised to the 3rd power. That's what the numerator means, raised to a regular power, and the denominator is the type of radical it is. We make it smaller first by doing the radical first, and the square root of 9 gives us 3. Then 3 to the 3rd will give us 27. Subtracting 4 from both sides of the equation leads to x equal 23. Now we can think about this. Does this work? 23 plus 4 is 27. Raised to the 2/3 power, the 1/3 power represents the cube root. The cube root of 27 is 3, and 3 squared is 9. So it definitely works. Oops, we've forgotten a number. Let's see what number we've forgotten and what mistake we've made. What process did we go through that might have introduced another possible solution? Let's look back and check it out. Scrolling back up, let's go through the steps and let's see what we might have made the mistake on. Looking at this, we have it equal to 9, then we raise both sides to the 3/2 power. The 3/2 power represents the square root and then cubed. Oh yeah, I forgot. When I put in the square root, it has to be a plus or minus. If it's an odd radical in the denominator, then we don't have to worry about the plus or minus. But if it's an even radical, we have to put in the plus or minus. This should have been plus or minus the square root of 9 raised to the third power. Then we have plus or minus 3 raised to the third power, which gives us two possibilities. This gives us x plus 4 equal 3 to the third, and x plus 4 equal negative 3 to the third. When we have negative 3 to the third, we're going to get a negative 27. So x plus 4 equals negative 27. Then we subtract the 4 from both sides, and we get x equals negative 31. Let's test it and see if that's the error that we made. Indeed it is. So what have we learned from this? Whenever you take an even radical of a number that was not originally in the problem, you have to introduce the plus or minus. If the radical is already there at the beginning, you don't have a plus or minus. We saw that in the radical equations at the beginning of this section. If the radical is already there, you don't put in a plus or minus. If you put in the radical and it's even, 2, 4, 6, 8, and so on, then you have to put in a plus or minus. Let's take a look at another type of problem. In this particular problem, we have x to the fourth minus 17x squared plus 16 equals 0. We don't normally solve ones that are the fourth degree, but we can solve this one because even though it's not a quadratic equation, which has the highest power being 2, but it is like a quadratic equation in the way that it solves itself. In other words, this first term is x to the fourth, and the middle term is x squared, which tells me that the x to the fourth is going to split up into x squared and x squared. Because the middle terms came out to be the same, they added, so they had to both be x squared terms. If they weren't both x squared terms, they wouldn't be like terms and they wouldn't add together. That means that x to the fourth has to factor as x squared times x squared. Now let's think about the 16. We know from this last sign being positive that the signs in the middle of the binomials will be the same. And we know that we'll be taking a sum. We need two numbers that multiply to give us 16, but add to give us 17. Well, that's pretty straightforward. It's got to be 1 and 16. Let's try it. Remember that this says they're the same, and this then says they're both negative. Let's test the product. Negative x squared and negative 16x squared gives me negative 17x squared. That is what I have in the middle, so I know it works. I use the intuition method to solve this one. These kinds of equations are what we call quadratic in form. They're not really quadratic equations because quadratic equations, the highest power is degree 2. This is degree 4, which is much higher. However, it behaves like a quadratic equation in the way that it factors. Now, when we're looking at this one, we can solve it by setting each of the factors equal to 0 and further factoring it. We could also do it in the form that it's currently written in. Let me rewrite it so that we can see the factoring directly below each piece. Now, if we had this, we could then do the factor of x squared minus 1 is x plus 1, x minus 1. Remember the difference of two squares pattern. If you have a squared minus b squared, you get a plus b, a minus b. X squared minus 16 is also the difference of two squares. So we have x plus 4 and x minus 4. Now we can solve this by setting each of the factors equal to 0 using the zero product property. This would give me x plus 1 equals 0, or x minus 1 equals 0, or x plus 4 equals 0, or x minus 4 equals 0. This gives me different solutions of x equal -1, x equal 1, x equal -4, and x equal 4. I think I got all of those in there correctly. And these would be our solutions to this problem. Let's put them in and see how we did. Excellent. Let's take a look at the next problem. Well, actually, let's back up a minute. What if you couldn't get it to factor? Could you use the quadratic formula or completing the square? Yes, you can, but you wouldn't get x. You would get x squared, the middle term. Let me show you what I mean. Let's start back at the original problem. We had x to the 4th minus 17x squared plus 16 equals 0. What if you had trouble factoring it? Maybe the numbers were worse than this one. Well, you would still have to recognize that x to the 4th would have to factor as x squared and x squared. But then you could use the quadratic formula where you pull a to be 1, b to be -17, and c to be 16. But instead of getting x equal, you get x squared equal the opposite of b plus or minus the square root of b squared minus 4ac, with each term divided by 2a. Now I would find b squared minus 4ac, the discriminant, separately. This would give me -17 squared, which I believe is 289. Check for me. Minus 4 times 1 times 16. Now 4 times 16 is 64. So I have 289 minus 64, which would turn out to be 225. I have pretty good confidence in that because I already know this problem solves and the answers are integers, -1, 1, 4, -4. This is a perfect square, which tells me that I will get rational numbers for my answer. Now putting this into the parts of the quadratic formula, I have x squared equals the opposite of -17 is 17, divided by 2 times 1 for a, plus or minus the square root of 225 for the discriminant over 2. Now the square root of 225 is 15. So this gives me 17 over 2 plus or minus 15 over 2, which I can split into two different parts. 17 over 2 plus 15 over 2, and 17 over 2 minus 15 over 2. 17 plus 15 gives me 32 over 2, which equals 16. 17 over 2 minus 15 over 2 gives me 2 over 2, which reduces to 1. Remember that because this was quadratic in form, we weren't actually looking for x, we were looking for x squared, the middle term factor. And that tells me that if x squared equals 16 or x squared equals 1, now I need to solve it using the square root property. The square root property, it's not there already, I'm putting it in. So I have to remember to put in a plus or minus. And that gives me my plus or minus 4 and my plus or minus 1. So yes, it can be solved using completing the square or the quadratic equation. It's just a little bit more complicated in that you're not getting x, you're getting x squared. Let's take a look at another problem. In this problem, it's also quadratic in form, and I'll show you a couple of ways of approaching this one. When we're looking at this problem, number 16, we have 5 times the quantity t minus 3 raised to the second power plus 10 times the quantity t minus 3 equals 0. In other words, this is quadratic in t minus 3. Now, some people like to do what's called a u substitution, and they let u equal t minus 3, and then they rewrite the equation that's 5u squared plus 10u equals 0. We could have done this on the last problem and replaced x squared with u, and then we would have had a quadratic equation in u. How does this help? Well, I can solve this for u and then back substitute for what u is. How did I know to pick t minus 3? Well, t minus 3, if it were the variable x, would have given me a quadratic equation. And since the t minus 3 is identical in the two pieces, that's what told me to use it for u. Now, looking at this particular problem, I don't have a constant term. If I don't have a constant term, it's not going to factor as the product of two binomials. That means that probably I'm looking for the greatest common factor. Looking at these two terms, I can definitely take out a 5, and they both have at least one u. This one only has one, so that's the most I can take out. When I divide 5u squared by 5u, I get u left behind. Remember, that's what factoring really is. It's a form of division. 5u squared divided by 5u is u. When I divide 10u by 5u, I get 2, because 10u divided by 5u equals 2. Now I've got two things multiplied together equal to 0. After doing the substitution step, I can then solve using the zero product property. This means that either 5u equals 0 or u plus 2 equals 0. If 5u equals 0, I can divide both sides by 5, and that gives me that u equals 0. The other equation gives me that u equals -2, but I'm not looking for u. The original problem was in terms of t, so I'm looking for t. So then I make another substitution and I back substitute. U was t minus 3. This is called a back substitution because you're going back to what you originally had. Back substitute for u. U was t minus 3. So t minus 3 equals 0, or t minus 3 equals -2. Now I can solve each of these equations individually, and I get t equal 3, or adding 3 to both sides here, I get t equal 1. That's two solutions, 3 or 1. I haven't done anything that was risky, like squaring both sides, so I don't have the possibility of extraneous solutions. Now, I said there's another way to do this one, and there is, but it's long and tedious. What is the other way of doing this? Well, we'll call this the brute force method. The brute force method simply looks at the problem and says, well, I've clearly got some polynomial equation. I'm going to multiply everything out. When we multiply everything out, some students are tempted to want to distribute the 5 over both sets of parentheses, but that's not how it works. Think about how you multiply three numbers together. If I write 2 times 3 times 5, you don't do 2 times 3 and 2 times 5. You just take a pair and multiply them together and then multiply by the third number. So that's what we do with polynomials. We're going to multiply these two together first, and then we'll multiply by the 5. So the 5's just hanging out. T times t gives me t squared. On the outside, t times -3 gives me a -3t, and I get the same on the inside. This is just the distributive property. -3 times -3 gives me +9. On the second term, 10 times t minus 3, I do distribute the 10 over both because I only have two factors, 10 and the binomial t minus 3. That gives me 10t minus 30 equal to 0. Now I want to add my like terms in the parentheses before I distribute the 5. If you leave enough space, you can write directly above or below it, and you don't have to rewrite the whole thing. I didn't quite leave enough space, so I'm going to rewrite the whole thing. Then we distribute the 5 over each of the terms on the inside. I promise you, if you will write those arrows, you will never mess up the distributive property again. It is one of the most missed properties in not just college algebra, but in calculus. So get into a good habit and start drawing those arrows. This leads to 5t squared minus 30t plus 45 plus 10t minus 30 equals 0. The balance point is on the right side where the equals is. That's right here. That means that everything on the left is already on the same side. We simply need to combine our like terms. I have 5t squared. That takes care of that term. I have a negative 30t and a plus 10t, which combine to give me negative 20t, which takes care of those two terms. And 45 minus 30 gives me a plus 15. Still equal to 0. Note I did not move them from one side to the other because they're on the same side. Now I need to solve this quadratic equation. The first thing I want to note is that they're all divisible by 5, so I can definitely get rid of the 5. If there were a t, I would factor it out, not divide by it. Don't divide by the variable. You lose a solution when you do that. So now I'm going to divide each of these terms by 5. Does it change the equation? Yes. Does it change the solutions? No, because I'm dividing both sides of the equation, including the 0, by 5. This keeps it balanced and keeps the solutions the same. Now I have a much simpler equation to solve, which is t squared minus 4t plus 3. When I factor it, it will factor as t and t. Signs are the same, and they're both minus. Why are we always getting all these same signs? Where are some with negatives? Then 3 can only split up as 1 and 3. Does it work? Negative 1t, negative 3t adds up to negative 4t, which is what we have in the middle, so it did work. Now we use the zero product property. The zero product property is going to set t minus 1 equal to 0 or t minus 3 equal to 0. Then solving each individual problem separately, I get t equal 1 or t equal 3. Is that what we got before? And was this process shorter? No, this process was definitely not shorter. The first process was much shorter. And I did get the same solutions, 1 and 3. The next problem is very similar to the previous problem, and that you have x plus 5, the quantity squared, minus 9 times x plus 5 again, minus 22. You can make a u substitution for x plus 5 and write a quadratic equation in terms of u squared minus 9u minus 22. And then you can factor that or complete the square or use the quadratic formula. This ends this video on this material. And the next video, we'll be talking about section 2.7.